semester to all students. So welcome to chapter 3 on liquid extraction. So we have finished on chapter 2. So now in this video I will explain on the chapter 3, which is liquid extraction. Okay. So at the end of this lesson, at the end of this topic, you should be able to first define the liquid extraction process, okay, and you should able to define what is partially immiscible system and what is immiscible system. Okay, in liquid extraction system or liquid extraction process, we have two types of situation, or we have two types of system. Okay, we call it partially immiscible system and immiscible system. Okay, so later I will explain on the differences between these two systems. Okay, next, at the end of this topic also you should be able to describe the ternary phase diagram. If you can still remember on chapter 2 distillation process, we use graphical method to determine the number of stages. Okay, so the same thing goes for chapter 3 with liquid extraction. We will use graphical method, and we call it we call it as a ternary phase diagram, a very important diagram. So we can also calculate the number of stages using this diagram. Okay, next we will you should be able to calculate the single stage liquid extraction. Usually for single stage we want to know the composition. Okay, the composition because of it is a single stage. Okay, so we will use ternary phase diagram to know the composition of the system or the liquid extraction. Okay, next you should be able to perform the mass balance calculation for the multi-stage counter current flow system in both partially immiscible and also the immiscible system. Okay, so in this liquid extraction we have two types of stage. We have single stage, we have multi-stage. Okay, and in multi-stage we have two systems. We have partially immiscible system and we have a immiscible system. Okay, so this is the flow diagram for the liquid extraction. Okay, so liquid extraction, the unit tower, it can be big, okay, but not as big as distillation column. Okay, so what is actually a solvent? Oh, sorry, what is the actually of liquid extraction? Okay, so this is definition and the application of liquid extraction. First, okay, the transfer of solute A of a liquid B by contact with another insoluble liquid C. Okay, so liquid extraction will happen like this. Okay, for example, I have a component A and B. Okay, for example, I have a component A and B here. A and B. Okay, and I want to separate A from B. Okay, A and B exist as a liquid because this is a liquid extraction. So the both A and B come as a mixture in form of liquid. Okay, in liquid extraction, I want to separate A and B. So I will use another liquid. I call it as component C. It comes in form of liquid. So this is what I call it as a solvent. So this is liquid C as solvent. Okay, so what happened? Okay, in this system, A, B and C will mix together, and C will extract the component of, for example, I want A. Okay, so C will extract the component of A here as a product, and B will be separated, will be left out. Okay, so this is how the definition, this is how the liquid extraction happen. Okay, so the transfer of component A from B into C is based on the preferential solubility. Solubility of solute A in C. Okay, so it will this component A will transfer into C. The factor that makes the A move to C is we call it as solubility. Okay, preferential solubility. Okay, two streams result from this contact. We have extract and raffinate. Okay, so what is extract and what is raffinate? If I can draw, okay, again. Okay, for example, I have component A and B. I change. Okay, I have component A and B here. This is the feed. Okay, I call it as a feed. So I want to separate A from B. So I will use the C as a solvent to extract A. Okay, so C is the solvent. So as a product, so this is solvent. So as a product, C will extract the component A, C plus A. Okay, so the product, this is what we call extract. Okay, so B will leave the system as the byproduct, and we call it as raffinate. Okay, so this is what we call raffinate. So what is raffinate? Raffinate is solvent-rich solution. Okay, so containing the desired extracted solute, which is solute A. While raffinate is the residual phase solution, which is the B. It usually will contain a little volume of A. Okay, B plus A, but it's A. The amount of A is very little. Okay. So this is the liquid extraction principle. Same like I explained. Okay, this is in form of diagram. So this is the solvent. The blue liquid is the solvent. So this is the liquid mixture. Okay, organic solvent containing solute A and B. Okay, so I want A. So I will do a mixing or stirring, shake or stir, to allow the molecule to partition, okay, to mix, to react together. Okay, so when they mix thoroughly, so the solvent will extract the solute A. This is solute A, this is solute B, for example. Okay, so A prefer to soluble into solvent, so solvent C, so C will extract solute A, and it will left with solute B. So this is what we call extract, and this is what we call raffinate. Okay, so this is what happened when we have a test tube or flask. We have these two solvent and the liquid mixture. We shake together, so and the solvent will extract the solute A. Okay, so what is immiscible? So immiscible is situation where the two liquid cannot mix together. So the immiscible cases here referring to these two solvent, means solvent cannot be dissolved into the feed cannot be dissolved or mixed with solvent, only the solute will transfer. Okay, so that what we call immiscible, cannot mix together. Okay, so if the solvent can mix with the feed, okay, or the liquid mixture, the liquid extraction cannot happen. Okay, so the application of liquid extraction used in food processing, pharmaceutical, and oil purification. Okay, so this is only the some example of the application. Okay, it can be more. Okay, so you can later you can read, and you can know the application the other application of liquid extraction. But usually the liquid extraction will be used in food and pharmaceutical and also oil purification. Okay, we have learned about distillation. Okay, and just now I just explained about liquid extraction. So somehow you can see the differences between liquid extraction and distillation. So as you can see, liquid extraction, it will depend on the solubility between the liquid component, and it will produce a new solution. For example, I have a mixture A and B. I want to separate A from B, and I have a solvent here. Okay, so the liquid extraction will depend on the solubility of A into C. Okay, so then it will become a product. We call it C plus A. So C plus A is a new solution. Okay, later we will separate this and we will get A only. Okay, but in distillation process, the process will depend on the boiling point, or we call it volatility. Okay, relative volatility, alpha AB, and also depends on the pressure of the substance. Okay, and distillation also requires heat supply, but liquid extraction does not require heat. Okay, so this is the differences between LLE and distillation process. Okay, so this is type of liquid extraction process. Okay, this is the type of solute, carrier. Okay, solute, usually this is component A lah. Okay, carrier is component B, and this is the solvent or the component C. Okay, this is the list of the LLE example. Okay, for example, if I have acetic acid and water, I want acetic acid. Okay, I can use solvent ethyl acetate as the solvent to extract the acetic acid from water. Okay, so this is how we read this list. Okay, so what is the advantages of liquid extraction over distillation process? Okay, as I mentioned before, liquid extraction does not require heat. Okay, so this process is actually suitable for recovery of heat sensitive material. For example, if we are dealing with a pharmaceutical product, so they cannot be heated, so very sensitive with heat, so we can use liquid extraction. Okay, next, if we have mixture, we want to separate, and the component have close boiling point, we cannot use distillation process. The alternative is we can use liquid extraction. Okay, so the separation of mixture, which is its relative volatility mu to unity. So this is, we call it as azeotrope. Okay, azeotrope you cannot use distillation process, but you can use liquid extraction. Okay, so this is azeotrope. If distillation requires excessive amount of steam generation. Okay, if we have a mixture, we want to separate, but the separation using distillation will use a lot of steam. Okay, when you use a lot of steam, it will increase your cost of manufacturing. Okay, so in order to reduce the cost, we can use LLE as an alternative. Okay, so last but not least, the advantages of LLE is solvent recovery, easily maintained, and energy saving can be realized. Okay, so for example, if I have component A and B here, okay, I have A and B, this is C, sorry. Okay, so C here, it will become product C plus A. Okay, C plus A. So this we will further separate. Okay, we will separate the C from A. So this is what we call solvent recovery. Okay, so the separation of C from A, to get A, we have to separate the C or the solvent. So this process actually is very easy. Okay, easy to maintain and require low cost and energy saving. Okay, so this is the differences between distillation and extraction. You can read by yourself. Okay, when the question comes comes out in the final assessment, you can use this as your answer. Okay, so when we talk about liquidity extraction, okay, so the key to get a good liquidity extraction is we have to choose a good solvent. Okay, so if the solvent cannot extract the solute that we want, so the LLE will fail. Okay, so we must choose solvent that is very good in extracting the solute that we prefer. Okay, so this is the criteria of the solvent selectivity. Okay, for example, the distribution coefficient. So I think we can, there is a lot of criteria that you can choose. Okay, so this is some of the example you can read by yourself. Okay, so this is the distribution coefficient. Okay, what is distribution coefficient? This is the ratio of the concentration of solute in the extract and the affinity. So it will give measure of affinity of the solute for the two phases. So distribution coefficient is actually telling you how much the solute A, affinity, the affinity of solute A towards the solvent. Okay, affinity tu macam dia suka tak dengan solvent C macam tu. Kalau solute A dia suka sangat dengan solvent C, maksudnya LLE tu berjaya. Okay, so that called distribution coefficient. Okay, so you can read by yourself. Okay, so this is another criteria, we call it selectivity or the separation factor. Okay, so this is selectivity of the solvent, defined as the ratio of distribution coefficient of A to distribution of B. Okay, contoh, for example, if we have component A and B, we want to separate A from B, we want to use C. Okay, so the selectivity or the separation factor, you must choose solvent that is more you should choose a solvency that is soluble to solute A. Okay, you want solute A, so you should choose a solvent that is more soluble for A but not B. Okay, so you have to choose based on your preferred component. If you have A and B, but you want A, but the solvent that you use is prefer to soluble with B, so you cannot choose this solvent. This is what we call it as selectivity. So insolubility of solvent, so you also must check the solubility of the solvent, which is it good? Okay, if the insolubility is low, the solvent should have a low solubility in the feed, otherwise the separation is not clean. Okay, for example, if we have, okay, this is solvent, this is the feed which is contain A and B. Okay, so the solvent must have a low solubility with the feed. If the solvent is soluble in feed, so the separation will not be successful, and we call it as not clean. Okay, so because the solvent can be soluble into the feed. Okay, the good thing is you should select a solvent with low solubility. Okay, so this is recoverability, density. Okay, recoverability. Okay, you should choose solvent that easy to recover. Okay, recover means if we have A and B here, C, so C will extract A, so this product will be further separated, we call it as solvent recovery. Okay, so you should choose solvent with good recoverability. Okay, so the density, okay, so you should also consider the density of the solvent, the pressure tension, okay, the chemical reactivity, the solvent should be stable, okay, stable chemically and inert. Okay, don't choose solvent that have the can be react with your feed. Okay, so this is all you can read by yourself. I think. Okay, viscosity, the vapor pressure, and the freezing point of the solvent. The cost, of course, choose a very cheaper solvent. Okay, and other criteria it can be toxicity and flammability and the stability of the